Hello, let's go and solve a very simple problem. We go to the problems section and pick up a property evaluation problem involving a perfect gas model. So let's pick up problem number 346. As you can see in this problem, what's going on? Hydrogen is heated from 20 degrees Celsius to 200 degrees Celsius. It is kept in a container of fixed volume and a fixed amount. So very simple problem. If you want to learn a little more, you can click on this animation which shows the process on a TS diagram. What happens to entropy as the temperature increases? We know entropy does increase with temperature. Now let's go and first try to see if we can solve the problem manually. Because I'm logged in as an educator, I have access to the solution manual, and as you can see, it's a pretty straightforward problem. We are using the ideal gas equation here. So PV equals mRT. M is given, temperature is given, volume is given. We don't have to explicitly find pressure, but yeah, we could, but we can find the change using this formula. Change in energy is given by essentially change in internal energy, because change in KE and PE are negligible, and therefore it's simply a matter of finding CV. Same with entropy. So if we know CV and R, then we can find all these desired answers. So let's go see where we find those properties. We go to the property tables, and if we go to the perfect gas model, click on common gases, and it will come up with value of R, value of CV for hydrogen, as you can see right here. We can pick up the desired properties. Now let's see how we can verify the solution using a suitable test calc. We go to the test calcs module, and it's about finding properties of states of a closed system. So we go to the system state and launch the PG model right here, and go to the test calc test app tab. First thing is to select the gas, and let's enter the properties we know. We start with 20 degrees Celsius. I believe mass was 1 kg and volume is 2 meter cube. That's sufficient information that calculates the pressure. Let's go to state 2, for which we know the temperature, degrees Celsius, and because it's a closed tank, mass doesn't change. It's a rigid tank, therefore volume doesn't change. Now, if we wanted to enter more properties, suppose we said, okay, let's try to enter pressure, you will see you cannot enter into input mode. It doesn't turn yellow, and it tells you a message that the property P can be evaluated from others that are same would be the fate of if I click anywhere else. It will tell us that we cannot enter any more properties. We have sufficient information for this state. Now that the state 2 is calculated, we can go to IO panel and pick up the desired answer by evaluating the expressions. Change in pressure, energy change will be simply M1 star E2 minus E1, and entropy change will be M1 star S2 minus S1. So notice that we have calculated the desired answer, but if you come to states, look at the state 1. The energy of state internal energy is negative. A lot of people get surprised by that. How can energy be negative? You got to remember that it's a relative value, just like height can be negative. We always measure elevation from a certain datum. So therefore, potential energy can be negative in that sense. So there's nothing wrong in energy being negative. It's always the change in energy that in thermodynamics we are interested in. That's what enters the energy equation. One more thing here, while we are at it, notice that phi and psi, these are exergy. For a closed system, phi is important, and for an open system, it's psi that is important. Notice that phi is not evaluated. That's because the dead state, which is the dead state is the state 0, designated dead state, is not yet known. Here, if we enter the atmospheric, the ambient condition, suppose it's 100 kPa and let's say it's 25 degrees Celsius is the ambient condition. If we enter the ambient condition, calculate the dead state, then you will find in state 1 and 2, exergies have been calculated. So if you go to the I/O panel and find out the change in stored exergy, M1 star phi2 minus phi1, and calculate that, that is a very meaningful property. It says that the amount of useful energy stored in the tank because of this heating is only 379 kilojoules. All these units are automatically SI units as stated here. And notice that the change in exergy is much less than change in energy. So that's something you have to understand. The exergy is the useful part of the energy that is stored in the system. In other words, you can convert 379 kilojoules into electricity directly if you have a efficient system. That will be the maximum limit of useful work you can get from this heated tank. A couple of other things. Suppose we click the super calculate button, then it does many things. First of all, as you can see here, you see a table of properties calculated and the states that are calculated on a TS plot. You can switch the plots into something else you like if you want from this menu. And in the I/O panel, in the output area, you will see a detailed calculation report. And in the input area, you will see test code followed by all the equations that we manually entered. So this could be a record of the solution. You can just copy and paste it in a Word book or in a notepad or something for future use. If you want to regenerate the solution, put the states, paste them back here and click the load button. And what happens is that all these variables are read, and then you can come back here and reuse these states. I'll just let you go and play with some of these test steps. There are more capabilities that are being built into them every day. But let me just tell you this, that when you click super calculate, it doesn't automatically update all states. You have to go manually update the states. Suppose the gas is not hydrogen. Suppose the gas were carbon dioxide. In that case, notice, if you go to state 1 and we make it carbon dioxide, you calculate, you have to come back to state 2 and calculate again. And now if you come back to I/O panel, you can calculate these equations very easily. Redo this calculation by clicking this calculate button. Pretty soon we'll have a global super calculate which will automatically update everything. We are not doing it at this time because it's quite computation intensive, and for the time being we want to first make sure we have all the capabilities of Java applets built into the test steps before we turn that feature on. So see you in the next solution.